Hi, welcome back again. My name is Jake Rigby, and I'm very glad to announce our next presenter, Mattia Brenner. So, over to you to talk about navigating the design space.
Yes, thank you very much, Jake, for the introduction. The title of my presentation is Navigating the Design Space. And what is meant by that is how to quickly identify optimal ship designs for a set of complex requirements in a large, wide design space. So I'm representing the company Friendship Systems, and we develop and license, of course, a software solution that is called Cases. And I would like to get started by saying a few words about Cases. So, what is Cases? First and foremost, Cases is a highly specialized CAD system that is intended for simulation and data-driven design of marine systems. It is focused on the efficient modeling of any type of complex geometries. Um, it's fully customizable uh, for the user to create tailor-made designs and workflows. So it's not a black box solution. There are certain boxes, but they're open boxes, and everything can be adjusted to the needs of the user. And as I said, the intention is for it to be used for simulation data-driven design. So the generation of variance is very important, and it provides a reliable variant generation in order to conduct design studies and optimizations. But Cases is beyond that also an automation environment that allows the integration of arbitrary simulation and calculation tools into the process. It's also an optimization platform that allows to run design explorations and optimization processes, and something that, of course, is gaining more and more traction and interest. It's also a valuable tool for the generation of training data for machine learning or AI models. So this is kind of the very quick overview. I'd like to look at some things in a little bit more detailed. And if we look at what does Cases provide, as I said, the first and probably most crucial component of Cases is geometry parametrization. So you can create fully parametric models of arbitrary geometries, in this context, specifically ship hull geometries, but also appendages, energy-saving devices, propellers, um, and so on. Um, it offers dedicated modeling workflows for some of these examples listed here that basically guide the user through the process of creating such a parametric model by also offering a wide range of components that can be pieced together. For example, for ship hull, things like foreship, aft ship bulb, SCAG in different variations that are um, pre-configured as parametric models, but again, everything can also be modified by the user and adjusted to their needs, and also created completely from scratch. And alternatively to creating a completely new parametric model, Cases also allows to morph imported geometry. So basically, parameterize changes to an existing geometry. If you have, for example, a parent hull that you would like to modify and optimize, then that would be one possible way to go. And I already mentioned variation. This is quite a crucial part. It beyond the pure modeling of the geometry, it offers the possibility to very reliably create variants of the geometry without failure to regenerate the model when changing parameter values or other geometry issues like distorted geometries and things like that. Efficient parameterization is also an important point, which means providing a high flexibility for shape changes using as little parameters as possible. And finally, It provides a simulation-ready geometry that is suited to be used directly for meshing and simulation, so that there is no need for manual preparation in between. And beyond the pure modeling to check the geometries that have been created, it also offers um, things like calculation of hydrostatics and intact stability, and the definition of constraints that are typical for ship design, like constraints on the hydrostatic properties, but also things like hard points and arrangements and so on. Yeah, the second component within cases is a generic interface that allows to couple arbitrary external analysis tools into the process by very easily defining the data exchange, so the input and output files that go out and come in to cases. And it allows to parameterize values also within these input files and extract result values from the result files to be used as objectives or constraints in the optimization process. And finally, the third component is the optimization platform that offers a wide selection of DOE or optimization strategies, either conventional methods or based on machine learning methods. It also allows to distribute computations on remote machines if you have a cluster or something like that. And also post-processing tools that allow the side-by-side comparison of geometry variance, flow fields, generation of reports, statistical analysis, and finally also the possibility to integrate into other optimizers. If you're using a third-party optimizer, cases can also be very easily integrated into that process. So to summarize or to conclude this introduction, just very quickly look at how the typical process looks like. So the process always starts by defining a parametric model of the geometry that we want to optimize, and integrating all the necessary constraints on the geometrical constraints in this case. Um, then the next step would be to interface to the simulation or calculation tool so that the geometry can be sent in an automated way to the calculation. And when we can do that, then we can start creating variants of the geometry, analyzing them, and thereby exploring our design space. And when we do that, then we can incorporate all of our design requirements, and then finally search and find the optimal solution using the different strategies, either conventional or machine learning methods. And in the end, the goal is always to reduce manual iterations and increase the efficiency of the design process. All right. So this was a little bit of an introduction. So we've seen what we do and a little bit of how it's done. So the next point that I would like to address is the why. And to do that, I would like to take a look at an application case. And what I've brought here today is an OSV design case study that was done by our customer Kongsberg Maritime in Norway. So this is an offshore service vessel, or more specifically, an offshore construction vessel that they worked on. And I would like to start this case study by looking at the challenges, maybe initially, let's say more general challenges that apply to any kind of ship design, not only this specific one. So we're dealing with a high dimensional, tightly constrained optimization problem, and the complexity of this optimization problem is driven by the geometry and the design feasibility more than by the, let's say, the mathematical setup of the optimization. And what yeah it's this kind of optimization task is also characterized by a complex set of requirements and constraints. So, for example, we were dealing typically with a certain operational profile of the vessel. So it's often not much use to optimize the vessel for a very specific operational point, but we have to take into account different operational modes, as we can see, for example, in this diagram. So we have maybe transit speed, we have dynamic positioning, standby, maybe different drafts, loading conditions, and so on, that all take up a certain amount of time that we want to take into account into when we find an optimal solution. Um, General arrangement is also of importance. The vessel has to fulfill certain requirements as to, for example, cargo space or accommodation space, or to be able to fit certain equipment within the hull. Um, there is usually constraints and requirements on the hydrostatics and the stability of the vessel, and so on. I think you all know uh, what these typical requirements and constraints are. And within this kind of regime that I've been talking about, it's often difficult to find the best compromise within the limited time that is available. For example, in the initial design process, or when submitting a tender for a certain vessel. As I said, we have a large, complex design space, and navigating through this design space is not easy, and to find yeah good solutions is not easy. So if we just approach it by randomly generating designs, many of them would be infeasible and will not fulfill these requirements and constraints. And using, let's say, a naive optimization approach will waste a lot of time and resources. And also specifically, if we look at the geometry, we want to be able to be very flexible, and in many cases, failures in the geometry are also taking up a lot of time and resources. If we stay just briefly about within the challenges and look more specifically at this case, as I said, we're dealing here with an offshore construction vessel with a large crane, as you can see as an example here in the picture. And this vessel must specifically maintain stability of the vessel during the heavy lifts of the crane. It must offer reliable station keeping to keep its position during these construction operations, and it should be energy efficient across all the different operational modes, like in dynamic positioning, but also in transit, sailing. Of course, decisions that we make early in the design process have far-reaching consequences for the building costs of the vessel, but also for fuel consumption and for the performance of the vessel in operation. And not very surprisingly, we have very interdependent parameters. So, for example, improving stability might negatively affect the resistance, or optimizing the hull form for sailing operation will influence windage and the demands for dynamic positioning, or the crane configuration impacts the vertical center of gravity and therefore the stability and feasible vessel dimensions, and so on. So it's not easy to find the right solution. And the solution that was set up here to address these challenges was to come up with a holistic, tightly integrated workflow that would link all these different relevant criteria together into a design loop, using cases as a hub, in this case in the middle. And what this does is basically that all requirements are automatically considered when we're running a design study. And yeah, all the designs and results that we get make sure that they take into account these requirements. All right. If we look at this process or the steps in this process in a bit more detail, so we can go through quickly one by one. The first step is the generation of the hull form. In this case, we're using the morphing approach that I've mentioned before. So parametric transformations of a parent hull design. Um, the transformations allow us to change things like, for example, the main dimensions or the displacement distribution, the bulb shape, and so on. And the output is, of course, the surface model of the hull and also first evaluation of the hydrostatic parameters of the hull, like metacentric height or longitudinal centers of buoyancy and flotation, wetted surface displacement, and so on. Then the second step that we go through for each design is the weight and loading estimation. So in this case, we're using an internal calculation within cases that was configured by the user to yeah, estimate the weight and also to adjust the operational draft according to the correct weight and displacement. And the input that we need here is yeah, some information about the arrangements, like the required cargo area, accommodation area, deck heights for accommodation, and some weight constants that yeah, were put together by Kongsberg based on existing vessels. And the output is the lightship weight, so the estimate of the lightship weight, the operational loading condition and vertical center of gravity, as well as the yeah, the initial stability, transverse initial stability, GMT. And this one is highlighted in blue because this is a hard constraint that is used within the process to, if this constraint is violated, then the process is interrupted for this design and then restarted with the next variant. And you'll see a few others of these blue highlighted um, values here. So step 3 is the calculation of the intact stability. So in this case, NAPA was used and interfaced with cases to evaluate the stability criteria and also perform a drop load calculation for the fully loaded crane. The input that is provided from cases to NAPA is the watertight model of the hull in IGES format, and the load and position of the crane, as well as the limits that we want to account for. And the output is the evaluation of the IMO 469 criteria, whether they're fulfilled or not. And again, this is one of these hard constraints, as well as the maximum heel and trim with the fully loaded crane. So the next step is a seakeeping calculation performed with the VERES tool from the ShipX toolbox. So this stands for vessel responses. And here the input that is provided by cases is sections, a set of sections for the hull and the hydrostatic parameters of the hull, some characteristics of the roll reduction tanks and the bilge keel positions, as well as the acceptable criteria for the crane motion. And the output here are the yeah, operability limits in terms of the significant wave height and period, and also the response, sorry, the RAOs, response amplitude operators, which leads directly to the next step in the process, which is the analysis of the station keeping. Again, these calculations are done with a plugin from ShipX station keeping, and calculated for two for intact condition and DP2 failure mode. The input are the RAOs and a few other um, properties of the vessel, as well as the arrangement of the propulsors. And as an output, we get the thrust for each propulsor in intact condition for the fuel consumption calculation, and the maximum required thrust in DP2 mode for the dimensioning of the thrusters. I think I need to speed up a little bit to finish these points. The next one is the resistance or powering calculation that was performed using a surrogate model based on CFD, pre-computed CFD analysis and empirical formulations, which provides the thrust required for sailing operation. And then the next step is the dimensioning of a thruster done with a user-defined feature within cases that will result in thruster selection. So it gives as an output for each propulsor the type, power, price of the propulsor. And as a next step, a fuel consumption calculation done with the DNV Cosmos tool for fixed power system configuration that provides then the fuel consumption for different engine types. And this then comes together in a cost estimation that it does a simplified cost calculation for the construction cost, this capex here, and the operational cost, construction cost estimated from the lightship weight and the propulsors, selected propulsors, and the operational costs purely based on fuel consumption here. And this goes through a multi-step optimization process that goes into different steps of refinement until it basically converges to an optimal solution for the given requirements. And the results here are a, let's say, balanced vessel design that fulfills the criteria of, efficiency and DP performance. And the selected vessel at the end had a construction cost reduced by approximately 5% and a fuel consumption reduced by about 6% with a verified operability and DP performance. And the benefits here were by using cases, the design team was able to rapidly investigate the full design space in this early phase of the design process, making sure that only feasible and balanced variants are considered in the process, reducing manual workload, and thereby being able to accelerate decision making in the early stage of the design process, as well as gain confidence in the selected design because all the options were covered and the performance well verified. And this also resulted in a fully repeatable, scalable workflow that can also be used for future OSV designs. Yeah, that brings me to the end of my presentation. I think there's a little bit of time for questions left.
Indeed. Thank you very much. I think we've got time for one very quick question. And the question that's been up there for a while was pulling from a comment you made earlier in the presentation. What is meant by simulation-ready geometry? Does that mean that you have the capability to clean geometry into beams and shells, etc.?
Beams and shells, maybe not specifically, because we're not dealing so much with a structural design in our tool. It's more on the hydrodynamic design, including maybe some other aspects, as was explained here. But generally, what I mean by simulation-ready geometry is that the export that comes out of cases during this automated process is something that can be directly fed into a simulation tool without the need to, for example, do manual cleanup or repair of the geometry, but also maybe where we define certain areas of the geometry that we need to assign certain boundary conditions or mesh settings to, and so on. So again, to summarize it, what is meant is a geometry that can be automatically processed by our downstream tool without the need of the user to interact at that point to do any manual preparation.
Indeed. Great. Thank you very much. And there are some other questions that we will send on to you afterwards, and you can discuss directly with
Yeah,
them.
brilliant. I'll
Thank
try
you very
to
much again for the
answer
great
them.
session.
Thanks.
Cool. Thank you.